If you really sit down and think about it, human communication is just, it's an absolute miracle of context.
Oh, totally. It's incredibly dense.
Right. Like, imagine you get a text message from a close friend, and it's literally just one word, 4 letters. The word fine.
Which is never just the word fine, is it?
Exactly.
Yeah.
Depending entirely on the unwritten context of your relationship in that exact moment, it changes everything.
Yeah, the situation dictates the reality of the word.
Like, is it a casual answer to "How was your day?" Or is it a reluctant response to a sincere apology? Or maybe a highly charged reaction to you accidentally backing your car over their mailbox?
Right. In that last case, fine definitely does not mean fine.
It really doesn't. That one tiny word means completely different thing. It could mean I'm surviving, or I am furious with you but politely suppressing it, or, we are officially done speaking to one another.
And as humans, we just instinctively read the room.
We do. We don't even have to consciously process it. We automatically understand this invisible web of meaning hanging between the words, but for the longest time, teaching a machine to do that.
Oh, it's impossible.
Yeah, teaching a computer to read the room wasn't just difficult. It was like the absolute definition of a computational brick wall.
It was the defining bottleneck of artificial intelligence for decades, really. Because computers, at their very foundational architecture, are entirely binary. They are deterministic.
They like rules.
Exactly. They demand fixed definitions. If a computer sees the string of characters FINE, it wants to assign it one specific memory address, one specific numerical value every single time.
Right.
A machine does not naturally tolerate ambiguity, yet human language is, it's constructed almost entirely out of ambiguity.
It's all we do.
Pretty much. The literal dictionary definition of a word is often the least important part of its meaning in a real conversation.
Okay, let's unpack this. Because we are going on a mission today for you, the listener, to completely demystify the core engine that finally solved this impossible problem.
It is quite the engine.
We are going to break down the exact mechanism driving the entire modern wave of artificial intelligence and large language models. We were talking about the attention mechanism.
A very big topic.
Huge! And our guide for this deep dive is an absolute masterclass from the educational series by 3 Blue 1 Brown. Specifically, we're looking at Chapter 6 on deep learning.
Which is just a brilliant breakdown.
It really is. The visual explanations in that source completely deconstruct the legendary 2017 Google research paper, Attention is All You Need.
The paper that started it all.
The very one. And my goal for you listening right now is this. By the end of this deep dive, you won't just know what an AI does to process text. You are going to have a visceral, aha understanding of exactly how a machine learns to understand context.
We're going to get right into the gears of it.
Exactly. We're going to look under the hood, no magic, no sci-fi tropes, just the pure mechanics of meaning.
And we are going to achieve that by stepping entirely beyond the typical tech bro jargon. We really want to look at the underlying geometry of meaning here.
The geometry of meaning, I like that.
Well, when you first encounter the literature on this topic, it sounds intensely intimidating. You hear terms like high-dimensional vectors and matrix factorization and multi-headed cross-attention.
Which sounds like something out of Star Trek.
It does.
Yeah.
But once you strip away the Greek letters and see the logical step-by-step progression of the math, it's actually beautifully, almost shockingly elegant.
So where do we start?
We are going to build this architecture from the ground up, starting from how an AI perceives a single isolated word, all the way to a massive parallelized system capable of grasping complex scientific truths and delicate poetic nuance.
Okay, the geometry of meaning. I want to hold on to that phrase, because to get there, we really have to start at absolute zero.
Right.
Before we can even begin to understand how words interact with each other in a full paragraph or like a text message, we first need to understand how an AI perceives a single word in total vacuum-sealed isolation.
Yes. Because an AI does not read the English alphabet the way you or I do.
It doesn't have eyes.
No, it doesn't. It's crucial to ground ourselves in the ultimate fundamental goal of the model we are studying. Whether we are talking about a sophisticated chatbot answering a medical query or a translation tool converting French to English.
Or even a system writing Python code, right?
Exactly. The core objective of this specific type of generative model, the transformer, is incredibly simple to state. It just takes a piece of text and predicts the next word.
That is it.
That is literally it. That singular, relentless goal is what drives billions of matrix calculations per second. But to even begin making that prediction, the model first has to ingest the text you feed it.
And it does that by physically chopping the text up into discrete pieces, right?
Yes, the input text is broken down into computational units called tokens. Now, for the sake of strict accuracy, in modern models like GPT-4 or Claude, tokens are very rarely whole words.
Right, they're like fragments.
Exactly. They're more often pieces of words, syllables, or common character groupings. So the word unbelievable might be chopped into un, believe, and able.
Which helps with typos and things, I assume?
It helps the model handle typos and rare words much more efficiently. But to keep the conceptual architecture we're discussing today intuitive for you to visualize, let's just simplify our framework.
Okay, sounds good.
Let's just pretend for the rest of this deep dive that a token is always just a whole, single English word.
Okay, so we have our prompt chopped into individual words. But at the hardware level, computers only process zeros and ones.
Right, they don't know letters.
They don't know what the letters DOG mean. They have no concept of a furry animal with 4 legs. So step 1 of a transformer is converting these tokens, these words, into numbers.
But it's not just assigning a random ID number, like giving the word dog the barcode number 502 and cat the number 503.
No, the architecture translates them into what are called embeddings, which are high-dimensional vectors.
What's fascinating here is how this initial embedding space fundamentally reimagines vocabulary. In basic mathematics, you should think of a vector simply as an ordered list of numbers.
Like coordinates.
Exactly. Mathematically, any list of numbers can also be interpreted as coordinates defining a location in a space. If you have a list of 2 numbers, say a 4 and a 3, that's a point on a standard flat 2D graph.
An X and Y coordinate.
Right. 3 numbers give you a point in our physical 3D space, length, width, and height. The embeddings used in modern large language models, however, don't just have 2 or 3 numbers.
They have a lot more.
They have thousands. We are talking about conceptual spaces with upwards of 12,000 distinct dimensions.
Which is just completely impossible for the human brain to picture visually. Like if you try to close your eyes and visualize 12,000 different directions all at right angles to each other, your brain just blue screens.
You literally can't do it.
You can't. But to make this intuitive, I want you to imagine this embedding space not as a physical room, but as a map. Think of it not as a dictionary with alphabetical pages, but as a massive, unimaginably dense galaxy.
A galaxy of meaning?
Yes. Every single word in the English language is assigned a specific GPS coordinate in this 12,000-dimensional galaxy. But here is the critical part, the breakthrough that makes all of this possible. The location of a word in this galaxy isn't random.
No, it's very deliberate.
The geometry of this space actually corresponds to semantic meaning.
The spatial relationships encode human logic. The specific direction you travel in this 12,000-dimensional space fundamentally changes the core concept of the word you are looking at. The 3 blue 1 brown source material highlights a classic brilliant example of this directional logic. Imagine you are floating at the exact coordinate for a masculine noun, say king.
Okay, I'm at the coordinate for king.
Through analyzing billions of sentences during its initial setup, the model has learned that there is a very specific directional vector, a specific mathematical path that corresponds to the concept of gender.
Okay.
If you take the coordinate for king and you take a mathematical step along that specific gender path in the 12,000-dimensional space, you don't just end up in empty space or at a random word like toaster.
No, you land squarely on the coordinate for the feminine equivalent, queen.
Exactly.
You can literally do algebra with abstract human concepts. You can take the 12,000 number GPS coordinate for king, mathematically subtract the directional vector that represents man, mathematically add the directional vector that represents woman, and boom.
The resulting set of 12,000 numbers will exactly match the GPS coordinate for the word queen.
That is so wild to me. And that's just one single direction. You can imagine how many other directions exist in this massive space.
Thousands of them.
There's a specific trajectory you can travel for plurality, like moving from cat to cats. There's a direction for geography. Moving from sushi to Japan is the exact same directional step as moving from pizza to Italy.
Or verb tenses, moving from walked to walked. The embedding space is a compressed mathematical topology of human knowledge.
It's beautiful.
It is. But, and this is the absolute crucial limitation we have to establish before we go any further. At this very initial stage, step 1 of the transformer architecture, these embeddings operate effectively as a static, isolated lookup table.
Meaning what, exactly?
Meaning they are completely and utterly context-free. The initial coordinate assigned to a word as it enters the system has absolutely no idea what words are sitting next to it in your
So
sentence.
wait, if I type the sentence, I sat on the bank of a river, the AI goes to its massive 12,000 dimensional map, grabs the single fixed coordinate for the word bank, and drops it into the sequence. But if I type a completely different sentence like, I deposited my money in the bank, it grabs the exact same coordinate for bank.
The exact same list of 12,000 numbers. At step 1, the model is essentially reading your sentence, word by word, with severe induced amnesia.
Amnesia.
Yes. It has a perfect encyclopedic grasp of vocabulary. It knows exactly where every single word lives on the master map and how it relates generally to every other word, but it has zero grasp of the immediate situation.
So it has no idea what's happening.
None. When it looks at the word bank, it has already forgotten the word river or money that you typed just a millisecond ago.
Oh, wow. It's like reading a complex novel through a tiny moving pinhole where you can only ever see one single word at a time.
That's a great way to picture it.
You recognize every word perfectly, but you have absolutely no clue what the story is actually about. And that problem is exactly what forces us to confront the great context conundrum.
The core issue.
Right, because if the initial embedding is just a static dictionary definition, a fixed GPS coordinate floating in space, how on earth does the machine know which definition we actually mean when a word is ambiguous?
Because ambiguity isn't an edge case in English.
It is everywhere. How does the model break out of that pinhole?
The source material provides a really fantastic set of examples to illustrate the severity of this conundrum. Let's take the word mole.
Okay.
Consider these 3 distinct phrases. American shrew mole, 1 mole of carbon dioxide, and take a biopsy of the mole.
Okay, those are 3 totally different conceptual universes: zoology, chemistry, and dermatology.
Exactly. When you and I hear those phrases, our brains process the disambiguation instantly. We know the word mole means a small, blind, furry mammal in the first phrase.
Right.
We know it's a highly specific scientific unit of measurement in the second, and a potentially dangerous skin blemish in the third. We do it seamlessly based on the surrounding context.
But as we just established, in step 1 of the transformer, the mathematical vector, the GPS coordinate, pulled for the word mole, is completely identical in all 3 of those sentences.
Yes, it's just a generic, middle-of-the-road mathematical representation.
It's stuck right in the center of all its possible definitions. It's holding zoology, chemistry, and dermatology all at once, but committing to none of them.
Precisely.
The 3 blue 1 brown video gives another great example to visualize this with the word tower.
Yeah.
If you just look up the initial static embedding for tower, it points to a very generic region in that 12,000 dimensional space.
Right.
It's a region generally associated with large, tall things, architecture, maybe concrete, maybe skylines.
But if that exact same word tower is immediately preceded in your text by the word Eiffel, so the phrase is Eiffel Tower,
Right.
that generic concrete vector suddenly needs to change dramatically.
It needs to move.
It needs to physically shift away from generic tall buildings in the mathematical space and move sharply toward concepts of Paris, France, European tourism, and 19th century wrought iron.
Wow.
Conversely, if the word tower is preceded by the word miniature, miniature, a tower of the vector, must fundamentally shift away from the foundational concept of being large or imposing.
So we have a mechanical problem here. How does the transformer actually yank that generic mole vector over to the chemistry department or pull the tower vector across the 12,000 dimensional galaxy over to Paris?
It's the central challenge.
We have these isolated points on a map. What is the physics engine that actually moves them?
The entire aim of the transformer architecture, and specifically the attention block we are dissecting today, is to progressively and mathematically adjust these embeddings.
Okay.
The network's singular job during this phase is to calculate a very specific mathematical vector, a trajectory, to actually add to the generic embedding.
It wants to push it.
Exactly. It wants to push that original context-free coordinate out of its generic middle ground and shove it toward a highly specific context-rich destination.
It's nudging it. It looks at the sequence and says, okay, you are currently the generic word mole, but I see the word biopsy sitting 3 spaces to your left.
Right.
So I'm going to mathematically calculate the distance to the medical sector of our map, and I'm going to push your coordinate exactly that far.
That is the exact mechanism. And crucially, it doesn't just do this once. It does it iteratively, allowing words to pass rich, layered information to one another over and over.
Oh, that makes sense.
To really visualize the staggering power of this progressive adjustment, the source material paints a beautiful mental picture. Think about reading the final page of a gripping mystery novel.
Okay.
Imagine reading an entire 80,000-word book, and the second-to-last sentence is, "Therefore the murderer was."
Oh, the suspense. I love it.
Now remember, the model's only fundamental goal, predict the next token, predict the killer's name.
Right.
The final vector in that sequence, the one sitting at the very end of the line, began its life simply as the initial context-free embedding for the word was.
Just a generic verb.
It's just a generic past tense verb. It contains no information about murder. But by the time the model is ready to predict the actual name of the killer, that single mathematical vector for the word was must have absorbed the context of the entire preceding novel.
Wait, really? The whole novel?
The entire thing. That one little dot on the massive map representing the word has to be nudged and pushed and pulled by every single clue, every whispered motive, every broken alibi in the entire 80,000-word book.
Until it finally lands on the exact, hyper-specific mathematical coordinate that points directly to the butler.
Exactly. It has to mathematically encode all the information from the full context window that is relevant to making that specific prediction.
That is mind-blowing.
But of course, processing a whole novel is vastly complex. If we want to understand the actual granular linear algebra of how these specific nudges happen, how the model decides what pushes what we need to scale down to a much simpler microscopic example.
Which brings us to the actual mechanics of the attention mechanism. How do words actually find each other in the dark to share this context? To achieve this context shifting, this nudging, words need a mathematical way to ask questions about their neighbors and find out who holds the information they need. Enter the core component, the single head of attention.
This is where we descend into the real machinery of the 2017 breakthrough. The 3 Blue 1 Brown video provides a running example that we will use to anchor this math.
Okay, what's the sentence?
A fluffy blue creature roamed the verdant forest.
A fluffy blue creature roamed the verdant forest. Got it.
For this specific example, let's suppose that the only type of contextual update we care about right now for this single attention head is having adjectives locate and adjust the meanings of their corresponding nouns.
Okay, keep it simple.
We want the properties of fluffy and blue to physically find the word creature and update its mathematical meaning.
Right.
We want verdant to find forest and update its meaning.
Right.
To execute this, the attention head introduces 2 brand new, vitally important mathematical concepts for every single word in the sentence: a query and a key.
Okay, queries and keys, Q and K. These are the famous matrices everyone talks about. Let's break down exactly what they're doing to the numbers.
Think of the query, the Q, as a highly specific question that a word is shouting out into its surrounding environment.
Like it's asking for help.
Exactly. For example, our noun, the word creature, wants to ask the sequence, "Hey, are there any descriptive adjectives sitting in front of me that modify me?"
Okay.
To create this query conceptually, the system takes the original, massive, 12,000-dimensional embedding for the word creature and multiplies it by a specific matrix of weights, which is called the query matrix.
And what the math is actually doing there, if I'm tracking the linear algebra from the source correctly, is that this query matrix actively compresses that massive 12,000-dimensional vector down into a much smaller, more manageable space.
It does.
It projects it down to, say, 128 dimensions.
That is the exact mathematical operation. It maps the word from the giant dictionary space into a smaller, highly focused query space.
A query space.
You can think of this resulting 128-dimensional query vector as the literal mathematical embodiment of the question, where are my adjectives?
It isolates just that one need.
Exactly. It has stripped away all the other information about the word creature and isolated just its grammatical need for a modifier. Now, simultaneously, while creature is forming its query, every other word in the sentence is generating a key, or a K.
So if the query is the question being asked, the key is the answer waiting to be found.
Conceptually, yes. The adjectives in our sentence, like sluffy and blue, need a mathematical way to announce to the sequence, I am a descriptive adjective and I am sitting in this specific position.
They need to advertise themselves.
Just like with the queries, the original 12,000-dimensional embeddings for fluffy and blue are multiplied by a completely different matrix of weights, the key matrix.
Okay.
This operation produces key vectors that are projected down to live in the exact same smaller 128-dimensional space as the queries.
Here's where it gets really interesting, and I want to visualize how these two sets of 128-dimensional vectors actually interact. Please do.
The source material talks about this matching process, and the best conceptual analogy I could map this to is like A highly organized, heavily structured singles mixer.
A singles mixer. Okay, let's run with that.
You walk into this party which represents the sentence. Every single person at the party gets two distinct name tags. The query name tag explicitly states what you are looking for.
Right?
So the word creature walks into the party, and its query name tag says, seeking descriptive adjectives immediately to my left.
A very apt visualization.
And then you have the key name tags, which proudly announce what you bring to the table. The word fluffy walks into the mixer, and its key name tag says, I am a descriptive adjective.
Okay.
The word blue walks in with the exact same key name tag. Now, they are in the room together,
Right.
but they don't just awkwardly stare at each other from across the punch bowl. To find out if they are a match, they have to compute a dot product.
Yes.
In linear algebra, the dot product is the literal spark of chemistry. The dot product is the fundamental mathematical operation for measuring how well a key vector aligns with a query vector.
So how does the math work?
The model takes the 128-dimensional query vector of creature and computes the dot product with the 128-dimensional key vector of fluffy. What the math is actually doing there is multiplying their corresponding numbers and summing them up.
Okay.
If those two vectors point in roughly the same direction in that 128-dimensional space, meaning the name tags match grammatically and contextually, the math of the dot product results in a very large positive number.
A high score.
Yes. In the specific jargon of machine learning, when this yields a high score, we say the word fluffy is attending to the word creature.
And what happens if they aren't a match? Like if creature tries to compute a dot product with the key vector for the word the.
The word the is a definite article, not a descriptive adjective. Because of how the network has trained its matrices, the key vector for the will point in a completely different orthogonal direction compared to the query vector for creature seeking an adjective.
So the math reflects that mismatch.
Consequently, their dot product will yield a very small number, or even a large negative number. This mathematically tells the system, these two words have zero relevance to one another for this specific grammatical task. Ignore this connection completely.
But the wild part is that this mixer isn't just people talking in pairs. Every single word in the sentence is computing a dot product with every single other word simultaneously.
Every single one.
Fluffy checks its chemistry with blue, blue checks its chemistry with the verb roamed, creature checks with forest. It is an exhaustively complete web of mathematical speed dating.
It is entirely exhaustive. To move beyond the mixer analogy and ground this in the actual computational architecture you'd see on a screen, you should visualize a massive grid.
Okay, a grid.
A two-dimensional grid of dots. The words of the input sequence are listed vertically down the left side, representing the queries. The exact same words are listed horizontally across the top, representing the keys.
Like a spreadsheet.
Exactly. Where every single row and column intersect, you calculate a dot product. That intersection becomes a dot representing the relevance score between that specific pair of words.
So if I trace row creature and intersect it with column fluffy, I hit a massive dot. Very high relevance.
Exactly. But if you trace row creature and column the slat, you hit a microscopic dot, or no dot at all. Extremely low relevance.
That paints a really clear picture.
By performing this exhaustive parallel calculation across the entire grid, the attention head mathematically maps out the invisible underlying web of grammatical and thematic relationships in a sentence.
It's quantifying what we just feel.
It quantifies the connections that we humans process intuitively in a fraction of a second.
Okay, so we have this grid. We mathematically know who is attracted to whom at the singles mixer, but we hit a major operational problem here.
We do.
The relevance scores on this grid, these raw dot products, are completely unbounded. The source material points out that depending on the vectors, these numbers can range from negative infinity to positive infinity.
Yes, they could be anything.
You might compute a score of 50 for fluffy and creature, a score of 500 for blue and creature, and a score of negative 12 for creature and thee.
Right.
If the AI wants to use these wildly fluctuating scores to actually mix meanings together predictably without the math exploding and destroying the model, it can't use raw, unbound numbers. It needs a strict proportional recipe.
And the consequence of trying to compute with those unbound numbers would be catastrophic for the neural network.
Why?
If you're baking a cake, a usable recipe doesn't instruct you to add positive infinity cups of flour and negative 12 cups of sugar.
Right, that's a terrible cake.
It gives you strict fractions, percentages, bounded ratios. The model is forced to turn these wild, volatile dot product scores into a perfectly normalized probability distribution.
Meaning everything is a fraction.
It demands that every value be squeezed between 0 and 1, and crucially, For any given word's row on that grid, all the relevance weights of the words attending to it must add up perfectly to 1.0.
And the mathematical device it uses to squeeze those numbers is a function called softmax.
Softmax is perhaps one of the most ubiquitous and critical functions in all of deep learning.
How does it work?
You take a complete row of the grid, say all the raw dot product scores of every word trying to relate to the word creature, and you pass that array of numbers through the softmax function.
Okay.
It uses exponentials, taking the mathematical constant e to the power of your raw score. What this effectively does is exponentially exaggerate the distances between the numbers and then squashes them into fractions.
Squeezes them down.
The large positive raw numbers, like the 500 for blue, become probability values very close to 1. The small or negative numbers, like the negative 12 for the SMEs, are crushed into values infinitesimally close to 0.
And it all adds up to 1.
Yes, the denominator of the softmax equation mathematically guarantees that the entire row sums to exactly 1.
So that wild, completely unmanageable score of 50 for Fluffy might be squashed down to 0.45. The score for Blue might become 0.45.
Right.
And the remaining 0.10 is distributed in microscopic trace amounts among all the other irrelevant words in the sentence.
Right.
It creates a perfectly clean, stable recipe. Attention model, to update the meaning of the word creature, use exactly 45% of the information from Fluffy, exactly 45% of the information from Blue, and negligible trace amounts of everything else.
That is the exact translation of the math into instruction. This finalized, strictly normalized grid of percentages is officially termed the attention pattern.
The attention pattern.
It is a flawless, mathematically stable map of who cares about whom. Now, there is a vital technical detail, the source material notes here, regarding a step that happens just before the softmax is applied, which is scaling.
Scaling.
Before those raw dot products are fed into the softmax function, they are divided by the square root of the dimension of the key in query space. So in our running example, that means dividing by the square root of a 128.
Wait, why do we need to shrink the numbers before we squash them? Doesn't softmax squash them anyway?
It does, but we have to manage how it squashes them. This scaling is implemented purely for numerical stability during the training process. Because softmax uses exponentials, if your raw dot products are too large, the exponential function blows them up so massively that the softmax output becomes rigidly binary.
Meaning it's just ones and zeros.
It pushes the highest value to an absolute 1.0 and everything else to a hard 0.0. When that happens, the network loses its ability to learn nuanced gradients. It's called vanishing gradients.
okay.
Dividing by the square root of the dimension acts as a mathematical thermostat, cooling the numbers down just enough so the softmax remains soft, allowing the network to learn a blend of contexts rather than just fixating entirely on one single word.
That makes a lot of sense. You want a nuanced recipe, not just 100% of one ingredient. But speaking of how the model learns, the source material brought up a completely different intervention on this grid that really made me pause.
Oh.
It's an operation called masking, or enforcing the arrow of time.
Yes, masking.
The video points out that during the training phase, to be computationally efficient, the model doesn't just read the whole sentence and then predict the very last word. It takes a block of text and predicts every single possible next token simultaneously.
That's right, for efficiency.
It predicts word 2 based on word 1. It predicts word 3 based on 1 and 2, all at the exact same time. But to make this work, it actively sabotages its own attention pattern grid. It forcefully puts blinders on the AI.
Blinders is a good word for it.
Before it even runs that softmax function, the system takes any spot on the grid that represents a future word relative to the current word, and it hard codes the dot product score to negative infinity.
Yes, it deliberately overwrites the math. So when that negative infinity is eventually passed through the softmax function, e to the power of negative infinity is squashed to an absolute, uncompromising mathematical 0.
But wait, let me push back on this because logically this feels counterproductive.
Offset.
If I'm reading a complex book, the end of a sentence very often completely recontextualizes how I understand the beginning. Human language isn't strictly unidirectional. Context flows backward just as much as it flows forward.
That is true.
If the ultimate goal of the AI is to deeply understand human language, why do we force it to wear these blinders? Why do we mathematically handicap it and block out future words with this masking?
Right.
Aren't we just teaching it to guess blindly rather than truly understand the whole thought?
This raises an important question, And the resolution requires understanding the stark difference between the final capability we want the model to have and the specific pedagogical trick required to teach it.
A training trick.
You have to remember the strict architecture of the training loop. The model is learning strictly via autoregressive sequential prediction. Its entire loss function, the mathematical grading rubric it uses to correct its billions of parameters, is based solely on its ability to predict word n+1 using only the sequence of words from 1 up to n.
Because if you let the math for word n peak at the embedding for word n+1 during the training process,
You wouldn't be learning the subtle predictive patterns of human language at all. It would simply be copying the answer key.
oh, wow, it would just cheat.
Imagine the model is trying to learn how to predict the word forest after processing the sequence. A fluffy blue creature roamed the verdant. If you allow the attention mechanism of the word verdant to look ahead and attend to the word forest that comes next in the training data, the network will instantly learn that the easiest way to minimize its error is just to copy the word it sees directly in front of it.
It takes the lazy way out.
It circumvents the hard work of learning grammar, logic, and context entirely. Masking forcefully enforces the arrow of time during training. It guarantees that the network is genuinely forced to learn the underlying, invisible patterns that naturally lead to the next word, rather than just cheating by looking ahead.
Okay, that clarifies it. It's exactly like covering the right-hand column of a vocabulary workbook with a piece of paper while you quiz yourself.
That's a perfect analogy.
If you can peripherally see the answer, your brain doesn't build the neural pathway to remember it. You have to force the blind guess to build the skill.
Exactly.
Now, before we move on to how the model actually uses this perfectly normalized masked recipe to change the meaning of words, the expert in the source video extrapolates on a massive hardware consequence of building this grid, this attention pattern. They call it the context bottleneck.
And it is the most significant engineering hurdle in the entire field of generative AI right now.
Really? The biggest one?
Because of how we construct this grid, where every single word must compute a dot product with every single other word, the computational size of this attention pattern grid scales quadratically.
Quadratically.
It is the square of the context window size. In computer science terms, it is an O of n squared operation. If you input a short prompt of 1,000 words, your grid is 1,000 columns by 1,000 rows. That requires calculating 1 million distinct dot products.
Which, to a modern processor, sounds trivial. A million calculations is nothing.
For short text, it is trivial. But what happens when you want to feed the AI an entire legal transcript or a massive code base or an entire 100,000-word book?
Oh.
Because the grid scales quadratically, a 100,000-word context window doesn't require 100 million calculations. It requires a grid of 10 billion dot products.
A billion.
If you double the size of the document you give the AI, you don't double the computational cost, you quadruple it. If you multiply the document size by 10, the computational cost multiplies by 100.
That's insane.
This geometric explosion in required memory bandwidth and processing power is the exact mathematical reason why large language models have historically choked when trying to read massive documents all at once. The exhaustive attention mechanism is brilliant for capturing context, but it is astronomically, punishingly greedy when it comes to computation.
It is a massive, heavy tax the hardware has to pay to achieve that deep semantic understanding. But for the sake of our deep dive, let's assume we have paid the tax.
We bought the supercomputers.
We have the supercomputers, and we have successfully built our perfectly normalized attention pattern grid. We look the grid, and we know exactly what percentage of the context from fluffy and blue we need to logically mix into the word creature.
Right.
But knowing the recipe isn't the same as baking the cake. A map is not the territory. Knowing that fluffy should update creature is not the same as physically altering the massive 12,000-dimensional GPS coordinate of creature so that its mathematical meaning actually becomes fluffier.
Right.
How do we execute the physical change?
To execute that physical change of the high-dimensional space, we must introduce the third and final matrix of this specific attention head, the value matrix, or the V matrix. We have exhaustively covered queries and keys. Now we finally arrive at values.
Q, K, and V, the holy trinity of the transformer architecture. I want to lock down exactly what the value vector is doing differently than the key vector. Let's go back to our word fluffy. We already established through the dot product grid that fluffy is highly relevant to creature, but what is the actual transferable information that fluffy needs to transmit?
To extract that transferable information, the model takes the initial massive 12,000 dimensional embedding for the word fluffy, and multiplies it by this third set of weights, the value matrix. This distinct mathematical operation produces a value vector.
Okay, if the queries and keys were the name tags at the singles mixer determining who's a match, what metaphor do we use for the value vector?
Think of the value vector as answering the prompt. If my key has been deemed highly relevant by another word's query, what exactly is the mathematical payload of context that I should deliver to fundamentally alter that other word's meaning?
So it's the actual payload.
It is the physical payload of context.
Let's elevate this to a digital editing metaphor because I think it maps perfectly to the math. Imagine we're editing a photograph in Photoshop.
Okay, Photoshop.
The queries and the keys, the dot products and the softmax grid, they are the masking tool. They scan the image and determine exactly which pixels need to be adjusted. They create the black and white mask that says, apply the edit here at exactly 45% opacity.
That's a great way to think of it.
But the masking tool itself doesn't change the color of the image. The value vector is the actual specific algorithmic color grade. It is the literal saturation curve, the exposure shift, the specific blue tint that is actually going to be mathematically applied to those selected pixels to change how they look.
That is a phenomenal conceptual mapping. The value is the actual mathematical color grade.
Okay.
So let's trace the final step for the word creature.
Walk me through it.
The model looks at the creature column in the completed attention pattern grid. It reads the strict recipe. It needs exactly 45% of the information from Fluffy.
Okay.
So it takes the newly generated value vector for Fluffy and mathematically multiplies every number in that vector by 0.45. It scales it down.
Right.
Then it looks at the grid again. It needs 45% of blue. It takes the value vector for blue and scales it by 0.45. It iterates through the entire sequence, taking the value vectors for all the other words, multiplying them by their microscopic fractional weights from the softmax, and it sums all of those scaled vectors together.
It meticulously blends the color grades.
Yes. This massive addition problem creates one final, seamlessly blended mathematical vector. In the 3 blue 1 brown source material, they formally label this resulting composite vector as delta E.
Delta E.
It represents the exact physical mathematical change in direction required. Finally, this delta E vector is literally added to the original context-free 12,000 dimensional embedding of the word creature.
Wait, just added, like simple addition.
Just added. Because it is vector addition, the coordinate physically moves. It is violently shoved through that high-dimensional space. The output of this entire operation is a brand new, highly refined, contextually rich vector.
So it's moved on the map?
It is no longer sitting in the generic center of the dictionary. It is a precise mathematical representation of a fluffy blue creature.
It is stunningly elegant. It's literally just matrix multiplication and addition, but it results in genuine contextual understanding. But the source material dives into a fascinating, highly technical nuance here about how this value matrix actually works under the hood.
Yes, the factorization.
Because we keep talking about these vectors living in a 12,000 dimensional space, and manipulating numbers that large across billions of parameters has to cause massive bloat in the model's memory, right?
The memory bloat would be catastrophic if executed naively. If you engineered a standard value matrix that took a 12,000 dimensional input vector and directly output a 12,000 dimensional payload vector, the size of that single matrix would be a 12,000 multiplied by 12,000.
Which is?
That is 144 million parameters. And remember, that is just for the value step of one single attention head. To save immense amounts of computational space and processing power, the engineers utilize a brilliant linear algebra trick called matrix factorization.
Explain the exact mechanism of that factorization. How do you shrink it without losing the meaning?
Instead of using one giant 144 million parameter square matrix, the architecture forcefully splits the value matrix operation into 2 distinct smaller steps. First, there is a value down matrix.
Value down.
This matrix takes the massive 12,000 dimensional embedding and ruthlessly compresses it down into a much smaller constrained space, let's say 128 dimensions, exactly like the keys and queries. This is where the actual payload of meaning is extracted.
Okay.
Then, after the blending step with the softmax weights occurs in this tiny 128 dimensional space, there's a subsequent value up matrix. This matrix takes that compressed, blended delta E vector and projects it back up, expanding it into the massive 12,000 dimensional space, so it is the correct size to be added to the original embedding.
So instead of mapping directly from 12,000 to 12,000, it is forcefully slicing the information through a tiny 128-dimensional bottleneck and then expanding it again on the other side. But how does that not destroy the data? If I compress a massive 4K video down to 144p and then upscale it back to 4K, it looks terrible. It's a blurry mess. How does the AI not lose the semantic meaning of the word when it squeezes it down to 128 dimensions?
What the math is actually doing there is enforcing a strict prioritization of information, which is a concept known as a low-rank transformation.
Okay.
When the model trains over billions of iterations using gradient descent, the value-down matrix is forced to learn how to discard irrelevant noise and keep only the most vital, foundational, principal components of the word's meaning that are necessary for this specific attention head's task.
So it's selective compression.
Exactly. It doesn't compress everything poorly. It learns to perfectly compress only the exact specific traits, like sluffiness, that it knows the value-metrics will need to reconstruct the relevant meaning later.
It's an intelligent compression algorithm that only saves the variables that actually matter for the edit it's trying to make. And the parameter savings are absurd.
They are profound. Instead of 144 million parameters, mapping 12,000 to 128, and then 128 back to 12,000 requires only about 3 million parameters in total. This factored approach brings the computational cost down by nearly a factor of 50.
That is a staggering optimization, but the source video pointed out a really funny little quirk about how this factorization is actually written about in the hardcore scientific literature versus how it's taught conceptually.
Yes, it's a structural detail that consistently confuses people when they first read the original array. Attention is all you need paper.
What's the confusion?
In practical compiled code implementation on the GPU, those second value up matrices from all the different parallel heads aren't executed separately. To make the hardware run faster, they are mathematically stapled together into one giant composite output matrix for the entire block.
Oh, I see.
So when you read a dense academic paper and it refers casually to the value matrix, it is usually only talking about that initial value-down compression step. It's a pedantic technical nuance, but keeping the parameter count incredibly low at this stage is absolutely critical for the architecture to support what happens next.
Right, because what we have just spent the last 20 minutes walking through the intricate dance of the Q, the K, the V, the dot products, the softmax normalization, the low-rank delta E projection, all of that beautiful, elegant math we just described.
There's just one head.
Exactly. It is just one single head of attention, which brings us to the true scale of this beast, the multi-headed hydra.
The multi-headed hydra is where the model transitions from a grammar checker into a seemingly intelligent entity.
Because adjectives, updating nouns, finding fluffy and applying it to creature is just one microscopic sliver of how human language functions.
It's just syntax.
Right. Language isn't just about subject-verb agreement or adjective placement. It's about subtle tone. It's about deeply ingrained pop culture references. It's about biting sarcasm. It's about abstract thematic associations that span across paragraphs. A single attention head, looking specifically for adjectives, is completely blind to all of that nuance. How does the AI simultaneously process the sheer multidimensionality of human thought?
It achieves that by running many, many distinct heads, entirely in parallel. This is the concept of multi-headed attention. A full attention block in a transformer doesn't just execute that QKV process once per word. In the architecture of GPT-3, for example, it runs 96 completely distinct attention heads inside each block simultaneously.
96 parallel processes running the exact same math on the exact same word at the exact same time.
Yes, but here is the critical distinction. While they're running the same algorithmic steps, they are not using the same numbers. Each of those 96 heads has its own completely unique, independently trained query matrix, key matrix, and value matrix. Because the mathematical weights inside those matrices are vastly different, each head learns to scan the 128-dimensional spaces for completely different contextual relationships. They produce 96 completely distinct, unique attention patterns.
Okay, this is where the genius of the architecture truly clicked for me. So Head number one might be the hyperspecific adjective to noun head we just discussed, looking purely at syntax.
Right.
But head number two might be looking for entirely different, deeply semantic, contextual clues. The 3 Blue 1 Brown video gave some brilliant examples of this abstract specialization. Take the word car.
A great example.
If the preceding words in the sentence are "they completely crashed thief," that implies severe structural damage and physical collision. So maybe head number two operates as an action-consequence head. Its specific queries and keys align to realize that crash modifies car, and its specific value vector forces the embedding for car to shift violently toward concepts of crumpled metal, deployed airbags, and insurance claims.
To take that a step further, look at how distinct heads can handle massive abstract entity resolution, resolving names based on thematic context. Take the proper noun, Harry.
Okay, Harry.
If the word wizard or wand or Hogwarts appears anywhere in the surrounding passage, even paragraphs away, one of those 96 attention heads will mathematically flag it. Its queries and keys will align perfectly, and its value vector will fundamentally shift the generic embedding of the name Harry to point directly, unequivocally, at the concept of Harry Potter.
But if the words Queen, Sussex, or William are hiding in the passage, a completely different attention head might trigger. Its matrices are tuned to British royalty, and it will yank the embedding of Harry entirely away from fiction, dragging it over to the real-world map coordinates of Prince Harry and the British royal family.
And the staggering reality is that all this contextual processing happens simultaneously. For every single word in your prompt, all 96 heads evaluate the context, and all 96 heads propose a mathematical change. They all generate their own specific delta E vector.
And then what?
The model's architecture simply takes all 96 proposed changes, sums them all together into one massive composite adjustment vector, and adds that to the original embedding.
So if I type a sentence into ChatGPT, for every single word I type, there are 96 separate, highly specialized internal monologues happening simultaneously in the background.
Yes.
One head is shouting, "I think this word is a noun." Another head is whispering, "I sense heavy sarcasm here," based on the verb. A third head is yelling, "This is definitively a Harry Potter reference," and they all just mathematically dump their opinions into a giant mixing bowl.
Mathematically, that is a highly accurate description of the parallel processing. Now, let's look at the sheer scale of the parameters involved. We established earlier that a single factorized head utilizes roughly 6.3 million parameters for its matrices. With 96 heads running in parallel, a single multi-headed attention block contains roughly 600 million parameters.
600 million tunable dials just for one single step of the contextual processing. But I have to ask a logistical question here, because visualizing 96 specialized heads is mind-boggling.
It is a lot to wrap your head around.
Do the engineers sitting at desks at OpenAI or Google sit down and consciously map this out? Do they write a line of code that says, okay, we need to program Head 42 to strictly recognize sarcasm, and we need to explicitly train Head 73 to memorize Harry Potter trivia, and Head 12 to understand French verb conjugations? How do human engineers know which head is doing what?
That is perhaps the most profound, unsettling, and fascinating part of this entire deep learning architecture. Human engineers don't explicitly assign these tasks. There is no human-written code that dictates a sarcasm head or a Harry Potter head.
Really? They don't program it?
Not at all. The model learns these highly specific, deeply nuanced behaviors entirely on its own from the underlying statistical patterns in the training data.
It's emergent behavior.
It is entirely undeniably emergent. When a model first begins training, the engineers simply set up the blank architecture, the empty matrices for the 96 heads, and initialize all 600 million dials with complete, random numerical garbage. They feed the model terabytes of human text and ask it to guess the next word.
And it just figures it out.
Initially, because its matrices are random, it fails spectacularly. But every time it guesses wrong, a foundational calculus algorithm called backpropagation kicks in. It calculates exactly how wrong the guess was, maps that error backwards through the calculus chain rule, and tweaks those 600 million dials by a microscopic fraction of a percent to make the error slightly smaller next time.
It is navigating an unfathomably complex, multi-billion dimensional loss landscape, just trying to find the mathematical valley where its predictive errors are minimized.
Precisely. And over billions of iterations, reading virtually the entire internet, these heads slowly self-organize. They naturally specialize because the mathematics of gradient descent dictates that having 96 heads look for 96 different specialized types of context is the most mathematically efficient way to minimize the error function.
That is wild.
The true behavior of these matrices, if you try to open them up and look at the raw numbers, is incredibly alien. It is completely illegible to a human. We can only interpret what they're doing by running experiments and observing the outputs, retroactively realizing, oh, it appears Head 42 has taught itself to track pronoun antecedents.
It's like we built the physical scaffolding for a mechanical brain, but we don't actually speak its internal mathematical language. We just gave it the immense capacity to learn and the unyielding objective to predict the next token. And the math naturally figured out that intimately understanding the lore of Harry Potter or recognizing the tone of sarcasm was simply the most mathematically efficient way to predict the next word in a Reddit thread.
Exactly. The structure provides capacity for intelligence, the data sculpts it.
Okay, so we have now fully constructed one massive 96-headed attention block. It's pulled in adjectives, it's pulled in pop culture, it's tracked pronouns, and it has refined the generic word creature into something incredibly specific, layered, and contextual. But, incredibly, despite all of that complexity, we are still not done.
We are just getting started.
Which means we need to zoom out and look at the whole skyscraper. Because in modern frontier models like GPT-3 or GPT-4, this massive 600 million parameter block we just spent the last 45 minutes exhaustively building is literally just a single floor in a towering skyscraper of computation.
The architecture is defined by its depth. The system doesn't just pass the words through one single multi-headed attention block and declare the job finished. A model like GPT-3 stacks 96 of these massive, multi-headed blocks consecutively on top of each other.
A 96-story skyscraper of pure context refinement.
Yes, and it is vital we don't skip over the structural glue between these floors. Interspersed between every single one of these attention blocks are dense feed-forward neural networks called multi-layer perceptrons, or MLPs.
MLPs. Okay, what do they do?
The attention mechanism's job is to move information between different tokens, allowing Fluffy to share data with the creature. But once that data is transferred, the MLP's job is to process that newly integrated information within the token itself. The MLPs apply nonlinear mathematical functions, allowing the network to compute complex logical combinations of all the new context it just absorbed.
So the attention block acts as the communication network, passing the notes between the students in the classroom, and the MLP acts as the individual student's brain, privately processing the notes they just received before the next round of note passing begins.
A perfect analogy. And this alternating process, attention, then MLP, attention, then MLP, happens sequentially 96 times. The initial sequence of words goes into block 1, gets refined. That newly refined sequence of vectors goes into block 2, gets refined again. It travels up all 96 floors.
It reminds me of the children's game Telephone, where you whisper a phrase down a line of people. But in this case, instead of the message getting degraded, scrambled, and confused with every whisper, the mathematical vector gets exponentially more profound, nuanced, and intelligent with every single layer it passes through.
And that progression of depth maps directly to a progression of abstraction. As the embeddings travel deeper and higher into the network, they imbibe increasingly nuanced, abstract context. Researchers who study mechanistical interpretability have found that in the first few layers, say layers 1 through 5, the attention heads are mostly just doing basic, localized grammar.
Right.
They're matching adjectives to nearby nouns, making sure verbs agree with subjects. It's structural.
But as you get to layer 50, layer 80, layer 90...
The embeddings have taken in so much cumulative context from the entire document that they begin capturing incredibly high-level conceptual abstractions. The later layers track underlying sentiment. They recognize tone, whether a passage is meant to be a mournful poem, a sterile technical manual, or a satirical essay. They track long-range logical dependencies and underlying scientific truths. The mathematical vectors at the very top of the network, right before the final prediction is made, don't really represent words anymore. They represent deeply complex, intersecting human ideas.
Let's do the arithmetic on the scale of this skyscraper, because the numbers are starting to sound like astronomy. We established we had roughly 600 million parameters for one single attention block. If we multiply that by 96 total layers,
You arrive at approximately 58 billion parameters dedicated entirely to the attention mechanism.
58 billion distinct mathematical weights perfectly tuned to extract human meaning.
And here's the kicker that often surprises people. That 58 billion is only about 1/3 of GPT-3's total 175 billion parameters.
Wait, really? Just a third?
The vast majority of the remaining parameters are actually housed inside those multilayer perceptrons, the student brains we just mentioned, sitting between the attention blocks. Even though the attention mechanism is the famous breakthrough that gets all the press, the sheer bulk of the network's memorized knowledge is stored in the feed-forward layers.
That scale is genuinely staggering to conceptualize. Now, before we wrap up the complete picture of this architecture, the source material briefly touch on a specific variation of this mechanism called cross-attention.
Yes, cross-attention.
Everything we've talked about up to this point is technically self-attention, where a single English sentence is looking at itself to find meaning. What exactly is cross-attention, and where is it used?
Cross-attention is a structural variation that becomes vital when a model is tasked with processing and relating two completely different sets of data. The classic foundational examples are language translation, say, turning a document from French into English, or audio transcription, like turning a spoken audio file into written text.
How does our singles mixer analogy work if there are two completely different groups of people who don't speak the same language? How do they compute the dot product?
It utilizes the exact same fundamental query, key and value linear algebra, but the inputs are forcefully bifurcated. For example, in an English to French translation model, the keys and the values are generated entirely from the original French text, the source material. They announce what they are and hold a payload of meaning.
Okay, that makes sense.
But the queries are generated from the English text that the model is actively trying to generate. So as the model prepares to output the next English word, that nascent English word sends out a query that effectively asks, which specific French words from the source document are most relevant to the translation I'm trying to perform right now? The French words provide the keys to answer that question, and the values to supply the necessary semantic meaning across the language barrier.
Oh, that maps perfectly. It's querying a separate database of meaning.
And notably, a key difference in cross-attention is that there is no masking required. There is no need to forcefully hide future tokens, because the entire source sequence, the complete French sentence you want to translate, is already fully known, fixed, and static. The model isn't predicting the French, it's just reading from it to predict the English.
So as we stand back and look at this massive 96-story architecture, I have to ask the multi-billion-dollar question. Why did this specific design, this attention is all you need paper from 2017, completely and utterly take over the technological world? Was it purely because the math was that much smarter and more capable of capturing nuance than the older AI models?
If we connect this to the bigger picture of computer science and economics, the true secret to the Transformer's absolute dominance, the real reason it conquered the AI landscape, is actually grounded in hardware limitations.
Hardware.
Yes. Before 2017, the dominant models for text processing were recurrent neural networks, or RNNs. RNNs had a fatal architectural flaw. They had to process text sequentially. They had to read word 1, finish processing it, then move to word 2, finish, then word 3. You physically could not start calculating the math for word 3 until the math for word 2 was entirely complete.
Which creates a massive computational traffic jam, a severe bottleneck.
A bottleneck that prevented scaling. The true world-changing architectural brilliance of the attention mechanism is that it is highly parallelizable. Because of how the grids are structured, all of those billions of matrix multiplications, the generating of queries, keys, values, and dot products for every single word in the document, do not depend on the previous word finishing first. They can all be calculated simultaneously, entirely independently of one another.
And that specific parallel architecture makes it the absolute perfect tailor-made software for modern GPU's graphics processing units.
Precisely. GPUs were originally designed to render millions of pixels on a screen simultaneously by doing thousands of simple matrix math operations at the exact same time. The Transformer architecture fundamentally unleashed the full latent power of modern silicon hardware. And as the source material astutely notes, perhaps the single biggest lesson in deep learning over the last decade is that scale alone, just making the models exponentially bigger, deeper, and feeding them exponentially more data, has driven massive, qualitative, unpredictable leaps in intelligence. The parallel nature of attention is what allowed us to scale up our compute in a way that was physically impossible with older architectures.
It is the ultimate perfect marriage of brilliant algorithmic design and sheer brute force hardware reality. And for anyone listening who wants to go even deeper into this hardware history or stare at the raw calculus behind the backpropagation we discussed, the 3 Blue 1 Brown video highlighted some amazing secondary resources.
Which they did.
They specifically recommend the deep dive lectures produced by Andrej Karpathy, the interpretability research from Chris Olah, as well as Vivek's historical breakdowns, and Britt Cruz over at The Art of the Problem. We absolutely second those recommendations if you want to keep exploring the math.
They are phenomenal, rigorous resources for anyone who wants to peer even further under the hood of these systems.
Okay, let's bring this all home. Let's do a quick retrospective of the immense journey we just took. We started in a cold mathematical void, a 12,000-dimensional vacuum, where words were just isolated, static coordinates, a generic creature, an ambiguous mole, completely frozen and blind to their surroundings, suffering from severe contextual amnesia.
And to cure that amnesia, we introduced the architectural matchmaker.
Exactly. We gave those isolated words queries, allowing them to shout highly specific mathematical questions into the void. We gave them keys to boldly answer those questions. We let them compute exhaustively parallel dot products across massive grids to mathematically define exactly who had chemistry. We took those wild, volatile sparks of relevance and forced them through the uncompromising vice of the softmax function, turning chaos into a precise, normalized, mathematically stable attention pattern, a flawless recipe of context.
And finally, we used the factorized value vectors to deliver the actual physical payload of meaning. We mathematically pushed, pulled, and shoved those original coordinates through high-dimensional space, iteratively refining them with the specialized nuance of 96 parallel heads, passing them up through 96 towering layers of attention grids and multi-layer perceptrons, transforming them from simple syntax to deep semantic abstraction.
We witnessed how raw, foundational math, just trillions of simple matrix multiplications and additions, can weave entirely isolated points of data into the rich, infinitely interconnected tapestry of human language. It is the architecture that successfully turns the cold, binary mechanics of a machine into an entity that can actually genuinely read the room.
It is arguably one of the most remarkable engineering achievements in human history. And frankly, it leaves us with a rather profound philosophical implication, one directly inspired by the depth of the source material we've explored today.
What's that?
We've just spent an hour dissecting how stacking 96 layers of simple matrix multiplication allows a machine of silicon and electricity to seamlessly grasp underlying scientific truths, to perfectly understand sarcastic pop culture references, and to sense the delicate, mournful tone of a poem. It is all just math, down to the final decimal point, yet the output feels undeniably, breathtakingly human.
It really does. It mimics our minds perfectly.
Which forces you to turn the mirror around and wonder, to what extent is our own human intuition that instantaneous, unexplainable feeling you get when you read a one-word text message from a friend and instantly know they're upset, just a biological algorithm? Our very ability to read between the lines? Is it entirely possible that our brains, with their billions of synapses, are just running an unimaginably complex biological attention pattern? Are we simply computing organic queries and keys in our own neural networks, pushing our own conceptual vectors through a high-dimensional space of lived experience? It is certainly something for you to ponder the next time you instinctively read the room.
Wow. From the simple, ambiguous text message fine to the biological, high-dimensional math of human intuition, that is an absolutely incredible thought to end on.
Thank you so much for joining us on this deep dive into the transform architecture and the true geometry of meaning. We hope you walk away seeing the invisible mathematical web between the words just a little bit clearer. Stay curious, and we'll see you on the next deep dive.